Well, here is kind of a doozy of a problem. Talk about Taylor series pushing your understanding. So it's a great one to watch just to get a sense. In 2010, this free response definitely gives you a sense of what Taylor series is all about. So here's a piecewise function where this is to throw you off a little bit. Basically, f of x is a piecewise function, but it's just filling in the undefined piece. So it's a nice function, except it's undefined at x equals 0. And for the function at x equals 0, there is a defined value of -1/2. So really, the function's cosine of x minus 1 over x squared, except when we put in 0 for x. So that's the biggest premise of this whole thing. The first question is just about 3 non-zero terms for the Taylor series for cosine of x, which is to be memorized, and you get a point for that. So you remember it's an even, cosine is an even function, so it even powers, and they alternate. So it's 1x to the 0, x squared, x to the 4th with their respective denominators. And then there's the general term. You can just start with 1. I put x to the 0 for emphasis. It doesn't hurt you at all. So that's one point. Then the next piece is we need to take that, and this is copying and pasting it, by the way. We need to take that and manipulate it to come up with a Taylor series for the function f of x that they give us in the beginning. And it's piecewise. Just really think of f of x as cosine of x minus 1 over x squared. So we just need to modify this known Taylor series to be cosine of x minus 1 over x squared. To get that to happen, the first thing we need to do is get that cosine of x minus 1. We do this a piece at a time. And we can actually get that just by subtracting 1 from both sides. That's it. Then the Taylor series just finishes off what we already know about -x squared over 2 factorial and so on. I can generate one more term so that I have 3 terms and then the general term. And nothing really changes about the general term except that we have this little issue of I need it to still generate the first term when n equals 0. So right now, if you look at the -1 is now to the n plus 1 because I need it to start negative. When I put in 0, I need to come out with -1. It also changes, when I put in 0, I need to get out x squared. So I also have to change x to be 2n because when I put in 0, but that's actually if I put in 0 for 2n, I'm sorry, that's not correct. That'll give you x to the 0, but we want it to be 2, so we just add 2. Denominator matches, so it's also 2n plus 2 factorial. So those are one of the things you have to make sure you can generate the first term by putting in n equals 0. So you have to modify the degrees of your general term so that it starts in the right place. It's the same formula, just modified. Then if you need to do the divided by x squared, we just run through everything divided by x squared. If you just imagine reducing the degree of each of those by 2, and we've got it. Then on the general term, same thing. We're reducing the x term by a degree of 2. Everything else stays the same, so now it's 2n plus 2 minus 2, which I'll just fix here really quickly. It just means we get 2n again for the exponent. We're done. That's the general term. Make sure you finish with a plus ... That's our Taylor series, 3 terms, and the general term for part A. It's just modifying cosine of x that we know and love and make it look like the function f of x. Even though they're piecewise, that little piece is just for one dot of it. You really just treat it like, that's just a special case for x equals 0. B is, would you please take now the derivative of f of x, if we need that, now we're dealing with this Taylor series, all we'd ever have to do in part B, and just remember, is to take the derivative of what we have. So just go in and take derivative of the constant, the very first term is 0, so we're dealing with the x squared over 4 factorial, its derivative. So I went through and found each term got its derivative. You'll see them kind of lined up like this. Those are all the derivatives lined up, and I'm going to get rid of that line there. There you go. But a derivative of that first term is 0, so it starts like this. There's our general term. I only did 2 in the nth term because I'm not done. That was just kind of one. I need to find f prime of 0 at that location. I need to evaluate this derivative at 0, and if I do, I notice I get 0. And the reason this is important is we're trying to determine if it's a min or a max. First thing I need is to show that the derivative is 0. That's part 1. The second, I just need to show that it's, I can do the sign test, or I can get a second derivative and show that it has concavity up or down, and that would indicate minimum or maximum. So we're going to go for the second derivative, because given the work that I have, it's pretty easy to take another derivative. So I'm going to go f double prime, put in 0, and see what I get. So let's get f double prime. Do another derivative. So here he is, f double prime of x, you get 2 over 4 factorial, negative 12x squared over 6 factorial. I'm only putting in a couple terms. And then the nth term, you always bring down the power and reduce it by 1. The constants, the 2n stuff, all stays the same. The only thing that changes is we're reducing the power of x by 1, pulling its power out front in the power rule. In this expression now for f double prime, I can plug in 0, and you can see it zeroes out everything except 2 over 4 factorial. And 2 over 4 factorial is 2 over 24, 1/12. That is greater than 0, so we have a concave up function. That means we have a relative minimum. And that's justification enough, just showing f double prime is greater than 0. Now you can say f of 0, f prime of 0, f of 0 is a relative minimum. Okay, part C. If I take this lovely function I've been working with, I'm just recopying it here just so I can work with it. This is my Taylor polynomial, my Taylor series for f. And if I want to mess with it, so I can use it for all kinds of stuff, even for like g of x is 1 plus the integral of f of x. You know, I can take the integral of f of x and use its term there, and that's what I'm going to do. If I want to know what g of x is, I'm just going to take the integral of the f portion of it and add 1 to it. So if you notice here, 1 plus, here's the integral of the f function I came up with from part A. And I didn't put in the general term because it says go to the 5th degree. So I stopped when I got to degree 5. And there we are. This is good. I can leave it like this, but you know, you can always clean it up a little bit. And by the way, I needed to really emphasize that at this point, since I stopped short, I wanted to put in the squiggles because it is an approximation. It is not exact. So there's my approximation of g. It's just 1 plus the integral up to the 5th degree of f of x that I found earlier. So then there's part D. Now D is a little bit of a bear, just because it asks kind of a funny question. It says, how can you show that the error, it talks about this being an alternating series, which we kind of already knew. It says, now this is what we have. I'm just taking what we have from the previous part of the problem. It says, would you get a 3rd degree Taylor polynomial? And by the way, you could generate a 3rd degree Taylor polynomial just by taking the first 3 derivatives, you know, of f of x as is, so that we can get this all figured out. And generate your own polynomial. You wouldn't have to do all this work we did before. You could jump right to part D and start generating your polynomial by doing derivatives. They're awful. They get quotient rule involved, and it's a messy process, but you could do it. It's not impossible. But let's just use what we have. Go to 3 degrees because they told us to. It says put in 1 and see what we get. Okay, so I put in 1. It's going to be off. Obviously, it's got error because it's an approximation. It's just doing a couple terms in the series, or the polynomial. And if I want to get these terms and add them up, I need a common denominator, make them all over 72, and ultimately we get 37/72. That's off. What we need to show is that it's off by less than 1 over 6 factorial. And if you remember for alternating series tests, you can get the estimate the error just by taking the next term in the series. So if I take the next term, that would be to that 5th degree that I had deleted earlier. So x to the 5th over 5 times 6 factorial, that's the next term in the series. But put in x equals 1 and see what I get. So if I do that, so error is just taking how far is it from the real deal, 37/72 from what g of 1 really is. We already know it's less than the next term in the sequence, 1 over 5 times 6 factorial, which definitely is smaller than 1 over 6 factorial. And we've proven the question they've asked. That's it, but quite the problem. Let me know if you have other questions.